a few extra after-hours lectures for graduate students.
Oh, excellent.
And then I would speed up here.
When would those other lectures?
I mean, so done, I thought I would have sort of additional kind of basic lectures after hours. So if you're interested, I want to get to something interesting, but I would like you to know the words I'm using, you know? So if you're interested in learning more about the analysis behind the gauge theory, let me know. Email me here, and let me know, and we'll try and schedule some time to do that. Okay, so remember last time, here was the setting. So we had this oriented connected four-manifold with Riemannian metric G. Then we fix principal G bundle. G's compact. Let's keep it simple. Lie group, so I think SO3, SU2, whatever. SUN, PSUN, whatever. Maybe E8. That would be fun. Well, one of these guys. And then you know, there's space of connections. That was an affine space. There's the group of gauge transformations. Bundle automorphisms. And then what we want to look at this quotient space and understand. There's a lot of interesting things to understand about the quotient space. So, you know, how far is it from being a manifold? Is it a dimensional manifold? And what's its algebraic topology? Now, let's think about this for 1 second. How far is it from being a manifold? So the important thing here is to construct, you know, sorry, and yeah. And then we had the anti-self-dual Yang-Mills equations, right? So if we have connection A, we've got its curvature. We're on a 4-manifold, so it decomposes into F plus and F minus. And we want to look at the kind of main player in our game, NP of X and G, is the set of gauge equivalence classes of connections that solve this equation. Right. That sits inside BP. So, so we want to see that essentially this is a finite dimensional smooth manifold. It's sitting inside here, and our sort of goal, in a sense, is to define something like a fundamental class of this moduli space in the homology of BP. You know, with suitable air quotes there. Now, yeah, so the first problem is that this action isn't free. Right, and so, you know, I mean, first there's, you know, it doesn't act freely. Well, if the center of G always acts trivially, so that's, if G has a center, then of course it doesn't act freely, but that's boring. This quotient still might not act freely. And and we characterize when that happens. That happens if, you know, let's say, so, well, so if you use a gauge transformation and A is a connection, then we can ask that this is the condition that this gauge transformation should be parallel with respect to the connection. That's if and only if U dot A is A. And let's let AP star, that's the set of connections, so that if dA of U equals 0, then that implies that U comes from the center. Then we can define the quotient space. And this is, with suitable completions, is a smooth infinite dimensional manifold with LPK completion if you know, K minus 4 over P is positive. Well, in fact, could be equal to 0, but that's a little trickier to prove. Okay? And so I say, yeah. So the basic step in the proof that this is a smooth manifold is the slice theorem. So, again, this sort of picture space of connections. We've got this G acting on it. Now, here's a connection. We want to construct a slice to the orbits passing through here, and just like in finite dimensions, a natural way. If you have finite dimensional manifold, if you want to construct a slice to the group action, you equip your manifold with a G invariant metric and take the orthogonal in the tangent space to the gauge, to the infinite, to the tangent space of the gauge orbit. And if you do that in the infinite, in this context, you end up with what's called the Coulomb slice. S at A, that's the set of connections of the form A plus little a, so the D star of A is 0. So this is the L2 orthogonality condition. To the gauge orbit. And the basic theorem is that if I take, let me decorate this with an epsilon, and if I make these variations sufficiently small, then the map G mod its center times the slice, which sends a gauge transformation and this connection to its image, well, yeah. So if I should have said this set A in here is called irreducible. Right. If A is irreducible, then this is a diffeo onto its image. Okay, and if it's not irreducible, then we can still say something. The way we should modify it. Remember, this center just always acts trivially. There's another thing it could have written here more generally that would still make it okay. I could take this. That's a Hilbert manifold. That's also, or Banach manifold, that's a Banach manifold. I could take the quotient by the action of the stabilizer of A. So the stabilizer of A acts here by acting by the inverse here and acting here. That doesn't do anything. That acts here, but when I move it to here, it doesn't do anything. So this gives me a well-defined map, and this is still a diffeomorphism. Right. So this is a version of the, like I was said at the end of the last lecture, this is a version of the sort of, basic theorem and transformation groups that what a neighborhood of an orbit looks like is the group mod the stabilizer times the slice, right? But the important thing is that finite dimensional theorem holds in this context. So now, having said that, we can now talk about the anti-self-dual Yang-Mills equation. So how do we think about the anti-self-dual Yang-Mills equation in this context? That's a, let's call it the map F. We'll call it F plus, that sends this guy to self-dual two forms with values in add P. Connection goes to its curvature. That's this curly F of A. So, this is going to be a map from LPK connections to LPK minus 1 connections. You're differentiating this guy. And again, with the usual constraint on P and K, this is a smooth map. And the fundamental observation here is that if I look at, remember, so the tangent space to the gauge group, remember, so gauge transformations are sections of the bundle, capital add P, and the tangent space to the gauge group, the Lie algebra of this guy, is sections of the little add P bundle. Right, so this is P across the Lie algebra, mod the adjoint action. This is P across the Lie group, mod the adjoint action. Right. And the fundamental sort of observation here is that if I look at, so let's write sections over X of little add P, that goes by the covariant derivative to 1 forms. The kernel here, what does the kernel mean? Just to see if anybody's actually paying any attention. Ajvath. You weren't paying attention. F.
Zero. It's the tangent space to the stabilizer.
Tangent space to the stabilizer. That's right. So the kernel of this is the Lie algebra of the stabilizer. If I linearize this guy, I get the d plus, and that maps to omega 2 plus of X with values in add P. So the observation is that I've got these operators, and d plus composed with dA, that's F plus A. So let's call this CA. If A is anti-self-dual, then that implies CA is a complex. D squared is 0. And the kind of theorem, which is basically due to a Tia-Hitchin-Singer, this is an elliptic complex. The index is 2p1 of add P evaluated on X, minus 2p1 plus the dimension of the Lie algebra over 2 plus the Euler characteristic plus the signature of X. All right. Now, so e.g., if G is SO3, then the fundamental representation and the adjoint representation are the same. So this is just, add P is just isomorphic to P. Just isomorphic to the vector bundle that you get by associating by the standard action. And, well, the formula is what the formula is. The dimension of G is 3 there. If G is SU2, there's a little more interesting thing you could do, because then you've got a vector bundle, a C2 bundle, using the fundamental representation. And then this guy has a second Chern class. There's a C2 of E, and you could ask, what is this? You could ask, what's the formula in terms of C2 instead of P1? And that's important to know. Or more generally, for SUN, just do it for SUN. Then you get a CN bundle. And then the dimension formula in terms of C, there's still a second Chern class. And the dimension formula is 4nk, and then plus dimension of SUN. Minus 1. Good. OK, great. So it's, sorry. The index, sorry. The index is minus this, even minus odd. One of those things. The thing that we really care about is the dimension, the kernel, the harmonic forms here, or the, that's the dimension, that's the tangent space to the moduli space. And its formal dimension is the negative of the index. What I wrote down was the formal dimension. Sorry. Let's do that. Negative index. Yeah, no, there are a lot of minus signs there, but they become, some of them become plus signs. So that's what it is in this case for SUN, but in terms of K, which is C2 of E on X. OK, great. Now, so the kind of hope is that this moduli space is a manifold of this dimension. D of P. So let's think about some examples. So we should have some examples. So we saw if X is the force sphere. We saw one example if we took if we took lambda plus of the four-sphere bundle of self-dual forms, that has the induced connection from the Levi-Civita connection is ASD. And with a little thought, you can convince yourself that actually this is a R3 bundle. There's no, so an SO3 bundle, or frame bundle's an SO3 bundle. There's no obstruction to lifting it to spin 3 or SU2 bundle. And this guy implies that if I look at the kind of Hopf bundle, this, you can see this in many different ways, but this admits an ASD connection, where what I mean by Hopf bundle is I think of this S7 as the sphere of two-dimensional quaternionic space, and I think of SU2 as SP1, the unit sphere of quaternionic space, and I let this guy act, so let's say G in SP1 acts on XY in this sphere by, today I'm saying it's by right multiplication. Tomorrow it might have been left multiplication. It matters. One of them's self-dual, one of them's anti-self-dual. But
why would you switch?
Why would you switch?
No, is there a real reason, or?
Well, one of them's self-dual, one of them's anti-self-dual.
Why would you want one versus the
other? Oh, we prefer to look at anti-self-dual connections because they're the ones that play well with Kähler geometry. They're the ones for which, if you have an anti-self-dual connection on a Kähler manifold, then first of all, it's holomorphic. The induced bundle has a holomorphic structure, and second of all, it solves the Kähler, the Hermitian-Einstein equation. So. Would you ever want a self-dual one? Well, you can always change orientation. So it's sort of, if you look at the literature, self-dual is where it started. 1975, Belyavov and Polyakov and Tupkin, when they discovered them, they were looking for self-dual connections, and that was great until somebody realized that, hey, that doesn't play well with Kähler geometry.
So the number of self-dual connections is less than the number of anti-self-dual connections.
Sorry?
So if you consider the number of self-dual connections, should that be smaller than the number of anti-self-dual connections?
Well, so don't forget that the Chern class of the bundle tells you whether it can admit a self-dual or anti-self-dual connection, right? So if self-dual connections have,
in a Kähler setting.
In the Kähler setting, no, but in a Kähler setting.
So if self-dual is a very rigid condition.
No. Yeah. No. Yeah. So. I don't, yeah, so, the story for, four manifolds, interesting four manifolds prefer one of its two orientations, like a complex manifold. And what you'll find is that, so on the one hand, if you pick, if it's Kähler and you pick the other orientation, for large Pontryagin class, there will be solutions for sure, even though you're looking at the wrong equation. Large, far away from zero with the right sign so that they can exist. However, when you try to count them in any sensible way of counting, the count will be 0. So they somehow, there's lots of cancellation, which we might see in some sense later. But anyway, so we've got this Hopf bundle. In fact, and the connection is just the most obvious connection on that bundle. The connection is the connection where you declare the horizontal space to be the orthogonal complement of the orbits, right? So this has an anti-self-dual connection, but the observation is that the ASD equations are conformally invariant. So, sorry, I should say. So that that implies that if I have this A naught on this on S7 over S4, and if I do here's S4, if I can do a conformal rescaling towards some pick a point on the sphere. And with some strength, I can do a tau. Let's call the point Z, not to confuse it with X and Y. Conformal, meaning in this case, say, I do a conformal change from this guy to R4, having this guy at the origin, and then I scale by lambda. But then the observation is that if I pull back my connection, this is also anti-self-dual, right? My A naught. So this is the standard one instanton. Right. Now, this. What do I say? Right. Now, the standard one instanton, because of its description, if I think of its curvature form, it's uniformly distributed, right? But once I start this conformal rescaling, then if I think of its pointwise norm, it's going to start concentrating at this point, and it will start to go to 0 away from that point. And so the observation then is that so I can.
This is a dumb question. How do we find the A naught?
A naught was, so A naught came from, we could think of it as coming from lambda plus by lifting it to the R3 bundle to an C2 bundle. But we could have just checked other ways that if I take just the connection on this Hopf bundle, which declares that, that thinking of S7 with its round metric, I've got these orbits, and I can define a connection by declaring the horizontal space to be the orthogonal to the orbits, right? So they turn out to be the same connection. And the second description, well, first description tells you that it comes from Levi-Civita connection, which is obviously invariant under isometry. So its curvature form is uniformly distributed relative to isometries. But these conformal changes keep the fact that it's anti-self-dual, but they obviously change, say, the way the curvature is distributed. And you see this bubbling phenomenon happening now. Right, so if I take this pullback of A naught, and I take the limit as lambda goes to 0 or infinity, doesn't matter, but say lambda goes to 0, then what happens to this guy? Well, this is, if I go back to R4, and here's the origin, and I've identified the origin with Z with the origin in R4, and I'm just doing this rescaling, then
With some section, so conform invariant, you are fixing the base remaining matrix.
yeah. Right. Just the base, yeah. You know, away from Z, the curvature of FA at some Z prime goes to 0, but at Z, let's call that AZ lambda. This goes to 0 here. On the other hand, I mean, you really have to do the computation to see this, but at Z, this blows up. So in particular, on S4 minus Z, this thing has a limit. Exists and is a flat connection. And in fact, on R4, I can write down a connection matrix for this guy. Writing it down in quaternionic notation, the A naught connection matrix for A naught is this guy. Connection matrix for a sort of 0 lambda is this that converges to that, which is which is sort of away from the origin, I can define a gauge transformation, which is unfortunately the conjugate of the, I'm thinking of R4 as the quaternions. Here, X is a quaternion, so I can define a unit quaternion away from the origin by dividing by its length. That's a unit quaternion. And this formula is, turns out to be this thing, GDG inverse, which means that it's a pure gauge transformation. So I can, so this flat connection extends so the limit connection. So it's important to notice that I took the limit of the connection, and I still get a connection, but it's only defined away from the origin. And it's not 0, but it's a gauge transformation of the trivial connection. Right? So the limit connection exists on S4 minus Z, but after a gauge transformation, Z is 0. I mean, Z is some random point on the sphere. Remember, this guy is defined by taking this random point on the sphere identifying the sphere minus its antipodal point with R4 and scaling. And then, so, you know, Z, when I put it in that picture, is 0, right? By definition of the picture, right? But after a gauge transformation, it extends. Extends to, but now a connection, well, the trivial connection, and the trivial connection only exists in the trivial bundle. Right. So what's important, you know, it's important to realize that, you know, I mean, this, if you do pseudo-holomorphic curves, this is a familiar bubbling phenomenon, but you know, it's important to understand how precisely it plays out in this context. It's not, you know, I mean, it plays out in a similar way, right? It's not like when you bubble, you have to do some kind of coordinate change here. You know, I mean, you know, when you bubble in pseudo-holomorphic curve story, you're changing the homology class of the pseudo-holomorphic curve. Here, you're changing the topology of the bundle. Right. So the basic theorem, Uhlenbeck compactness, plus the removable singularities, implies the following, that if I fix P, you know, so if AI is a sequence of gauge equivalence classes in a moduli space on MPX, sequence, then there exists a subsequence, you know, which after reindexing is still has the same name, converges away from finitely many points x1 up to xr in X. To a connection, well, converges away from many points, up to gauge transformation to a connection A in a bundle P prime over X, but well, gauge equivalence class A in some P prime over X where sorry, where how do I want to say it? Yeah, where the energy of A is less than or equal to the energy of A prime. Those are all the same. Those are minus 2 pi squared P1 of add P on X. And yeah, so what happened on the force sphere here is that we had something where the energy was, I mean, this guy's going to be, this guy's going to be a pi squared on the force sphere, and it's converging to something that has 0 energy. Okay. So again, the convergence is away from these points, but the removable. So you get a connection. In the first step, you get a connection that's defined away from the finite set of points as a limit, but then removable singularity tells you that that connection extends into some other bundle, and that other bundle, its characteristic class is somehow smaller than the characteristic class of the original bundle. Characteristic class measured in terms of the energy. Okay, so just like the bubbling and pseudo-holomorphic curves. Now, let's. Okay. Now, okay. So, and then another slightly. Yeah. Let's define an. An ideal connection is a pair of a connection. So I have in mind that I've fixed P already, but an ideal connection in P is a collection so it's A is a connection in some other, potentially other bundle P prime. This stuff you can think of as a point in some symmetric power of X. L is the sum of some of these K's. So these K's might be all one, and then it's just a point in the symmetric product. But so I don't care about the order of these guys, despite the fact that they're indexed by an ordered sequence. Sorry about that. That's a little sloppy. But you should think of it as a point in the symmetric product. How is all this supposed to be related? Well, I want the energy. So I want, the energy of A to be the energy of A prime plus some constant that depends on G times the sum of the Ki's. Okay, the constant here should be just working out so that, these guys you should think of as connections on the force sphere for the same structure group, and K is telling you about exactly which bundle on the force sphere you're picking up. So, sorry, anyway. could have said that a little better. But so, yeah.
I'll go first. There's a priori energy bound need for this.
No, I don't, because I fixed P. So because I fixed P, the energy of every connection is the same, right? That's it. Of course, important. I mean, and if I'm on a manifold with boundary, I need some more. I need more assumptions. But on a closed,
What is P?
P is the principal bundle.
Oh.
Yeah.
What is the on the right-hand side of the equation, it's V of A something? What is it at the bottom?
Sorry.
The E of A is equal to
Sorry. Sorry. It's just what I wrote. What I said was garbage. Thank you. What I wanted to say is that so this is the energy of a bundle of a solution to the anti-self-dual equations in P. This one, right? And I'm saying that this guy, which is a connection in some other bundle, together with some points with weights, that the energy of this guy is equal, it differs from the energy that it should have if it actually lived in P by essentially solutions that live on the 4 sphere, depending on the topology. The Ks are telling you the topology on the 4 sphere, yeah.
The Ks are supposed to be like direct deltas, like points.
I mean, so there are different ways you could have written this. I mean, I could, at the moment, I'm just thinking of them really as points in the symmetric product, right? But you could think of a point in the symmetric product as a sum of delta functions with integer weights. So, and that's not a bad way of thinking about it, because you think this measure is the limit, is the singular part of the limit measure of the connection, of the curvature, pointwise norm of the curvature. Yeah?
So is P prime just P with X, with the X1 through XR removed, or is it something more complicated? Is it over this symmetric? Is it a bond?
So P is, sorry. So, okay, yeah. Thanks. We haven't discussed the classification of bundles on 4 manifolds yet. And
So in standard model, Baldwin model,
Yeah,
so
yeah.
what is your P prime?
P prime is the trivial connection. So in the model, this is the trivial connection with the point being Z, with multiplicity 1. Right? Now, I should say a little bit more here. So, okay, but I will say it. So here, at the moment, I've only constrained P prime. This being a connection in P prime, its energy is given by this formula where this is add P prime. And so it's allowing the bubbling of at some number of points with some weights to the 4 sphere. What do I want to say? But there's another constraint, namely that, so P's are classified up to isomorphism by what? Well, first by P1 of add P. That's part of it. And second of all, if the Lie group's not simply connected by a class which I will kind of sloppily call W2 of P, which is a class in H2 of X with coefficients in the center of the group. And I want the P prime to have the same characteristic class in that case. Okay? I mean, in a sense, I don't have to. It's just not going to be a limit. right? And so Uhlenbeck's theorem, together with this definition and some more work, allows you to define the Uhlenbeck compactification. So that's the closure of this thing in the union of in this thing union P. So it's a disjoint union of these guys. And so, what do I mean by P minus 1? Well, for my given G, there is, I look at the smallest non-empty moduli space, smallest energy non-empty moduli space on the force sphere, which comes from the standard instanton by shoving SU2 into your group, actually. And then I can, I can form a new bundle by adding the orientation reversed guy to that. That's a way of decreasing the, So these P minus 1, P minus 2 are the bundles where that characteristic class drops by one sort of unit in the appropriate units. So this would be, if this was an SU2 bundle, then if this was Chern class K, this would be K minus 1, K minus 2. If it's, or SUN bundle, that you're just dropping the Chern class by 1 in this case. But if it's a G bundle, then you have to know what the constant is. Anyway, and as you drop by 1, you add. If you drop by 1, then you have 1 point on X. If you have drop by 2, then you have a point in the symmetric square. If you drop by 3, then it's symmetric cube. So that's the Uhlenbeck. We can topologize these guys by declaring that two connections are a connection here is close to a connection here if away from the points the connections are close and the energy of the connections near those points are appropriate for the given weight of the points. Right. So that, or so to say, if I think about it in terms of the delta function picture, that that this pointwise thing converges to Fa prime just the sum of these delta functions. Right. So the topology is, that guy. Okay. Let's do one thing. E8 plus E8 is not the intersection form of a closed form manifold. Okay? Rochlein's theorem says that's possible. How are we going to prove that? We're going to look at SO3 bundles over such an X, and suppose X Yeah, Q of x is E8 plus E8. Some tiny little bit of bullshit's going to happen here. But anyway, so you notice that this is, well, I'm going to make it minus E8 plus E8, or if E8's negative, whatever. I want this to be negative definite. Right? If it's positive definite, I take minus the manifold, so that's not a restriction. And then I pick a line bundle L so that C1 squared of L is minus 2. Right. And then I'm going to take my SO3 bundle to be the, or the corresponding R3 bundle, C to be L plus epsilon. Now, P1 of C, it is minus C1 squared of L is sorry, P1. I said formula was minus 2P1. Sorry. Yeah, sorry. Yeah, P1 is C1 squared of L. P1 is the is minus C2 of the complexification. Right. So minus 2. So the dimension of the moduli space for C on this X is 2P1, so 4 minus other characteristic plus signature is 1. Other characteristic plus signature over 2 is 1, so the dimension is 1. The observation, so is there a solution to the anti-self dual Yang-Mills equations on this manifold, this possible manifold? It's negative definite, remember? So is there a solution just in this line bundle? Ajvath.
There is.
Good. Why?
Because you prevent isoptimal two-form line.
Yeah. So it's curve. I take the harmonic form that represents its curvature because it's negative definite. That harmonic form is anti-self-dual. So this guy has it has a solution. So this moduli space is non-empty. Right. Now it's one-dimensional. Okay. Now that solution's the solution that we have is a little special because it's reducible, right? And so we'll do this a little more carefully next time, but the model near this, near the reducible is that the stabilizer of this, it's called the reducible A naught. The stabilizer is the circle. The index is 1, so it must be that the dimensions of the cohomology groups, that's H naught, H1, H2. I call this C because it's a representation of S1. It must be non-trivial, and it's sort of weight 1. So what the moduli space looks like near this guy is that it looks like C mod S1. So this moduli space looks like that near, which looks like R plus, right? So we have this picture. Here's our gauge equivalence class of A naught. Something leaves. Where can it go? It's a one manifold. It's got to be compact because if you bubbled, then the Pontryagin class would drop, this guy has this guy, the energy of this guy is sort of a half a unit in Chern classes. So if you drop, you're going to drop below 0. So this guy, this moduli space is compact. It's a compact one manifold. It has one boundary point. The only other possibility is that it might run into a different reducible. But then you have to do a little thinking and see that there's no other, there is no other reducible in this guy, in this MC XG. So we have a contradiction because we have a compact one manifold with one boundary point. There ain't no such thing. I mean, you have to think about this. That's a little thought about the, to think about the quadratic form a little bit. But anyway, okay, that's it for today. And yeah, so like I don't know if anybody came in late, but I thought I would give some maybe after hours lectures on actually some more of the analysis that we just brushed under the rug there. So if you want to do that, send me an email to my MIT email address, and we'll try and schedule a time if there's enough interest. Oh yeah. I forgot. Yeah, you can.